Electrical machine design. Good morning to all. Good morning to all. Electrical machine design subject. Topic: design of field winding. Design of shunt field winding. First point: cross-sectional area of the conductor of winding. Second: current in the winding. Third: number of turns in the winding. Fourth: proper arrangement of winding. Fifth: resistance of winding. Sixth: copper loss and the winding. Design of field winding. First point: cross-sectional area of the conductor. For small and medium-sized machines, round or circular conductors with paper insulation is used. For large machines, rectangular conductors are used. Resistance of the shunt field winding, or SH, is equal to VSH divided by ISH is equal to rho LMT FTSH divided by ASH. Design of field winding. Topic. First, cross-sectional area of conductor. ASH, area cross-sectional, that is equal to rho LMT F into ISH TSH divided by VSH. In problem, ampere turns given. Rho is 2 into 10 power minus 8, where LMTF is a mean length of turns of the shunt exciting coil or field coil. Design of field winding. Topic, that is cross-sectional area of the conductor. ISH and TSH, total field ampere turns per exciting coil on no load, that is ATF naught. VSH is equal to voltage across the shunt field coil. VSH is equal to bracket of 0.8 to 0.85 bracket V divided by P for generators, and VSH is equal to V divided by P for motors. Design of field winding. In this topic, design of shunt field winding. Mean length of turn. LMTF is equal to 2 into bracket LP plus BP bracket plus pi bracket DF plus 2TI bracket, where LP is equal to length of the pole, BP is equal to width of the pole, TI is equal to thickness of insulation bracket 0.8 to 1 cm, DF is equal to winding depth bracket 0.03 to 0.05 meter. Design of field winding. Topic, design of shunt field winding. Second topic, shunt field current. Cooling surface is equal to 2 into mean length of turn into height of the coil plus depth of winding. Cooling surface is equal to 2 into LMTF into bracket HF plus DF bracket meter square. DF is depth of winding. Permissible loss of the outer and inner cooling surface of the exciting coil is equal to 700 to 750 watts per meter square. Therefore, permissible loss in watts is equal to permissible loss in watts per meter square into cooling surface in meter square. Continuation of shunt field current. Therefore, shunt field current ISH is equal to permissible loss in watts divided by VSH. Third, total number of turns is equal to ampere turns divided by ISH is equal to AT divided by ISH. Design of shunt field winding. Fourth topic, number of turns per layer. TL is equal to 0.8 HF divided by DI, where HF is equal to bracket of height of pole minus height of shoe minus height of waster due curvature of yoke due to insulation. DI is equal to diameter of insulated conductor. For shunt machine, TL, that is number of turns per layer, is equal to HF divided by DI. Design of shunt field winding. Fourth point, number of layers is equal to number of turns in field coil divided by number of turns per layer. Resistance of the winding. Fifth topic, RSH is equal to rho LMTF TSH divided by ASH. Sixth, shunt field copper loss is equal to IS SH square RSH. Seventh, SF is equal to 0.75 bracket of D divided by DI bracket square. Electrical machine design. Good morning to all. Design of field winding. In this topic, design of series field winding. Finally, notice series field winding. Step 1. Ampere turns required for series field winding. ATSC series, that is AT series, is equal to bracket of 0.15 to 0.2 bracket IAZ divided by 2P. Second, current in the series field winding ISC is equal to IA. Third, calculate the number of turns per pole. TSC is equal to ATSC divided by ISC. Bracket rounded of nearest integer. Continuation of design of series field winding. Fourth, find out the modified ampere turns. AT series is equal to T series and I series. Fifth, assume suitable value for the current density. Del series is equal to 2 to 2.3 A divided by millimeter square. Continuation of design of series field winding. Sixth, area cross section of series conductor. ASC is equal to ISC divided by del SC. Seventh, make proper arrangement of turns in the space available for this winding, that is winding depth, 20% of the field coil height HF, and finalize the size of the rectangular conductor. Continuation of design of series field winding. 8th point, calculate modified area of the conductor with the size chosen. 9th, find out the resistance. RSC is equal to rho LMT SC TSC divided by ASC. LMT SC is equal to LMT F. 10th, series field copper losses is equal to ISC squared RSC. Electrical machine design. Performance of field system. First point, shunt field copper loss is constant irrespective of load. Second, series field copper loss is variable and is proportional to square of the load. Third, temperature rise depends upon losses, cooling surface and peripheral speed of the armature. Performance of field resistance continuation. Fourth point, theta is equal to bracket of 1400 to 1600 bracket PF divided by 1 plus 0.07 VA, where PF is the losses of the field system per unit cooling surface. VA is the peripheral speed meter per second. Theta should be less than 30 degrees Celsius.